our Unit 1 exam review. We did the first page in Part 1, and so we're going to start with max and mins. Whenever we're looking at max and mins, we want to think of them as extrema. So extrema is another word for maximums and minimums. And there is a difference between absolute and relative extrema. Absolute extrema means that there's no other point in the graph that either goes above or below, depending if we're talking about a max or a min. So let's sketch a graph and then we can label the different extrema on it. So I'm going to put an endpoint here and we're going to go like this. Let's look at that. So right away, I do not have an absolute maximum because this arrow will go on forever, never, never. So it'll never reach like an absolute point. I do have this point here. So my graph goes up, it hits that peak and it goes back down. This would be a relative maximum. I have to see that it is a maximum relative to both the left side and the right side. So around the graph or the graph around it. It is relative around it. This point here would be a relative minimum because again, it is a minimum relative to the pieces of the graph around it. It is lower than the parts on the left. It is lower than the parts on the right. This is not an absolute minimum because I do have a point that goes lower than that relative min. So this would be my absolute minimum because no part of this graph goes underneath that y value or that output value. This is an absolute minimum. This is not a relative minimum because it's an endpoint. I don't have the left side of this to compare. So a relative has to have your graph going to it and from it. I only have the right side of the endpoint, so that's not an absolute. So let's say I did take this graph and I just changed it and I made it so that it went back up. Now this point would be considered an absolute min because no point in my graph goes underneath it, and also a relative minimum. So this one counts as both. So this would be an absolute and a relative minimum. And I still have a relative max, a relative min, and then I don't have an absolute max because I have arrows that go on forever. Whenever we're looking at a relative extrema, so a relative min or a relative maximum, the rate of change at that minimum or maximum point is 0. So that instantaneous rate of change at that min or max is 0. So we're going to sketch a couple examples. We're going to sketch a graph that has one absolute max and two relative extrema. So it doesn't specify if it's a max or a min. Yours could look different than mine. Since I want an absolute maximum, I'm going to do something like that. So I have my absolute max. This would be a relative min and a relative max. So I have my two relative extrema and one absolute extrema. For this one absolute max and one absolute min. Since I want absolutes for both, I can't have arrows. So I'm going to start with an endpoint, and I'm going to go up to a maximum, down to a minimum, and I'm going to end on an endpoint. So this would be my absolute max, would be this one, and then my absolute min would be that bottom one there. If I had arrows where it would go down forever, this would no longer be an absolute min because my graph would go further. So is it possible to have multiple relative extrema? It is. We sketched some, so we can say yes. Is it possible to have multiple absolute maximum? It is not. You can't have multiple absolutes because absolute means it's a maximum or higher than everything else. The only thing you might think is if I have a graph like this where these are at the exact same y value, yes, there are two of them, but I have only one absolute maximum at a y value of whatever that y value is. So if I were to, let's just add a coordinate plane here. Let's say that's 2. I have an absolute maximum at an output of 2, and that takes 2 points, but it's still just one absolute maximum, one output value. Is it possible to not have an absolute extrema? Yes, it is. If I have like a cubic function and I have arrows on both ends, I would not have an absolute max or an absolute min. I have relative, but not absolute. Next, we're going to look at even and odd functions. One thing I want to emphasize with this, even and odd functions are different from even and odd degrees. So we can have an even degree function that's not an even function. Same way we can have an odd degree function that is not an odd function. So it's really important to know the difference between those. An even function, if we plug in negative x in for all of the x's, we would get out our original function. Excuse me. So we can say if you change the signs of x, then y stays the same. Oops. That's a really small line. I'm sorry about that. Even functions are thought to have y-axis symmetry. We should be able to fold it on the y-axis and have it line up. So if I have a graph that looks like this, it's like a W. If I fold it on my y-axis right there, it will line up. If I plug in negative x into all of the variables for the equation, they would all turn positive, and I would have the original function. It would be an even function. An odd function is when we plug in a negative x for everything, and we would end up getting the negative version of our original function. So if you change the signs of x, then y changes signs, and is thought to have 180 degree rotational symmetry, or 180 degree rotational about the origin symmetry. So if I have a graph, I would say this is an odd function. I could take this one side, rotate it 180 degrees, and it would line up with the other side. Next, we're going to look at zeros, which leads us into multiplicity. So for polynomial functions, we want to completely factor the polynomial and set each factor equal to 0. Factored form is when we have like parentheses like that, and we would have like x plus 1 or x minus something. So this would be factored form, and we can take each piece and set it equal to 0 to find our x-intercepts or our solutions. You could also factor until you get a quadratic. The quadratic itself might not be factorable, but then you can utilize the quadratic formula to find those remaining solutions. For rational functions, we want to set all the factors that are left over in the numerator equal to 0, and that will give us our zeros or our solutions or our x-intercepts. For multiplicity, multiplicity goes into our factored form, and we're going to label it on here and just jot some notes down. So this has a multiplicity of 1. It goes straight through our x-axis. So when we write out that factor, I have a solution at -3. It would show up as x plus 3 with a 1 exponent, which I don't have to write, but I want to include it so that we know we're talking about the graph. I have another x-intercept here at -1. This one, I'm going to make my arrow kind of long, has like odd multiplicity. We talked about it as having like a multiplicity of 3. Technically, it could have a multiplicity of like 5 or 7. We just generally don't really see that in math classes in high school, but it has an odd multiplicity other than 1. 1 is straight through. We're piercing it. This one, we approach it, we hover a little bit, and then we go through. It could come down the other way. So if we came down, hover, and then go through. So it's still going through the x-axis, but there's a little like hesitation here, which is making it the odd multiplicity. So for this example, we're going to say it has a multiplicity of 3. So it would show up as x plus 1, and then we would have a 3 as an exponent for that factor. And then remember, the reason that it looks the opposite is because I could set this equal to 0, and that's how I get -1. This last one here has a even multiplicity, or we're going to say a multiplicity of 2. It could be a multiplicity of 4, but we'll talk about it for 2. An even multiplicity means it's approaching the x-axis, it touches it, and it bounces back. So it changes direction. It could also come from the bottom, right? It could come up, hit it, and then bounce back down. Anytime it bounces and changes direction would have even multiplicity. So since our solution is at +2, in factored form, it'll look like -2, and we're going to say it has a multiplicity of 2. So if I wanted to write a factored form to match this graph, it would look like this. The only thing I would double check is my end behavior. So the positive, or the right side of my graph is going up, so it's positive, which means my leading coefficient has to be positive. Something else I notice is I have the arrows going in the same direction, which means I have to have an even degree. And so to double check, if I have a degree of 1 here, multiplicity of 3 here and 2 here, if I add those together, I get a degree of 6, which is even, which supports the fact that they are going in the same direction. We are going to move on to the last page so we can get them done in 2 parts. So the last one, we're looking at some transformations. So for transformations, our A value is our vertical dilation. That affects your Y values, which would affect your range. If our absolute value of A is greater than 1, then we would say it is a stretch. So 2, 3, 5, there's a vertical stretch happening. If our A value, or the absolute value of A, is in between 0 and 1, 1/2, 2/3, 0.75, we would say there is a vertical shrink or a vertical compression. The reason I'm using absolute value is because if A is negative, then there is a reflection across my x-axis. So I'm going to make a little note up here. If A is negative, we have a reflection across the x-axis. Next is our B value. This is a horizontal dilation, so horizontal stretch or horizontal compression. That will affect your x values, which affects your domain. If we have a B value, it is by the reciprocal. So for example, if B is 2, I actually have a horizontal shrink by 1/2. If B was 1/3, I would have a horizontal stretch by a factor of 3, because 1 divided by 1/3 is 3. My C is a horizontal translation, so either going left or right. If I have plus C, then it is actually going to the left. If I have minus, it's actually going to the right. It's kind of the opposite of what it looks like, and that will affect your domain. It affects your x values. And then our vertical translation is exactly how it looks. So if it's plus whatever number, it is going up. If it's minus whatever number, it is going down. So that does affect our range or our Y values. Next, we're going to look at rational functions. So for rational functions, it's important to know where their wholes are, where their asymptotes are. What is the rule for that? So a whole occurs anytime there is a common factor in the numerator and denominator that cancels out. So if we have a factor that's in both and it gets eliminated. So for example, if I had x plus 1, x plus 2, x minus 4, all over x plus 1 and x minus 3, I notice that I have x plus 1, which would cancel out. That means that I have a whole at x equals negative 1. Because I'm setting that factor equal to 0 to get that. A vertical asymptote occurs anytime that there is a factor left in the denominator. So if we actually look at the example I wrote over here, we removed the factor that canceled out, that's our whole. And so because x minus 3 would be left in our denominator, that means I have a vertical asymptote at x equals positive 3. So let's just make a little note here. We have a vertical asymptote at, not negative 3, at x equals 3. We always want to do this one after we figure out the wholes. We want to figure these out first, and then we can do our vertical asymptotes. Our slant asymptotes occur when the degree in the numerator is exactly one more than the degree in the denominator. So if the degree in my numerator is 5 and the degree in my denominator is 4, then I have a slant asymptote. So we can find a slant asymptote by doing long division or polynomial long division. And the slant asymptote is the quotient without the remainder. So whatever is on top of our long division, like house, the remainder is not a part of it. And that's how we get our slant asymptotes. For our horizontal asymptotes, there are 3 main ways to find it depending on our degree. So if the degree in our numerator is larger, we have no horizontal asymptote. If the degree in the numerator is exactly 1 larger, we have a slant asymptote. But if it's larger by like 2, by 3, there's no horizontal asymptote at all. If the degree in our denominator is larger, then we have a horizontal asymptote at y equals 0. So when the degree in our denominator is bigger, it approaches the x-axis, so horizontal asymptote at y equals 0. And then if the degrees are the same, so if the degree in my numerator is exactly the same as the degree in my denominator, I have a horizontal asymptote, but I need to figure it out. So we're going to say it's at y equals whatever the leading coefficient of our numerator is divided by the leading coefficient of our denominator. So we would divide those out. How I think about it is, I'll write it kind of in pencil. If I had like 6x to the 4th minus 3x over 2x to the 4th plus 2x squared, I kind of think of it as I don't pay attention to the smaller terms because the larger terms with the larger exponents will dominate what's happening. If you want to think of it as like x to the 4th will cancel out x to the 4th, these kind of go away, and so I'm just looking at 6 over 2, so I would have a horizontal asymptote at y equals 3. That's kind of how I remember it. And then at the very bottom of this, there's some important vocabulary that you should know. I just put them on there. Some of them are in the packet. One that I realize I didn't talk about is points of inflection. That is where your concavity changes. So if I have a graph like this, I have a point of inflection here, here, and here. It is halfway between a max and a min. And this would be concave down, this would be concave up, concave down, and concave up. So our points of inflection is when our concavity switches, which also has the steepest part of your graph. So like the fastest rate of change happens at your inflection points.